All right, so we're talking about section 5.3. This is where we're talking about another new kind of function. These are called logarithmic functions. What we're going to do here is we're going to take the two things that we talked about in section 5.1 and 5.2. So we're going to take the idea of inverse functions, and we're going to take the idea of exponential functions. We're going to put those two concepts together. What we're going to end up talking about is what the inverse of an exponential function looks like. Now, we didn't talk about those in section 5.1 because we hadn't talked about exponential functions yet. So to do this, let's go back to our really basic exponential function that we talked about in section 5.2. Probably the easiest one to deal with is if you have a function that's just like 2 to the x. So we did some function values for that. We put in some negative values for x. That gave us some fractions, and we put in 0 for x. That gave us 1. We put in 1, that gave us 2. We put in 3, that gave us 8. We're just looking at a few of these. Now let's think about what would happen if we looked at the inverse of this function. So remember the things that inverses do. One of them is that they switch the x's and the y's. If we take something with an xy table like this, if we had the inverse function and we did an xy table for that, all we would do would be switching these two. So if we put in 1/2 for x, we'd get -1 for y. If we put in 1 for x, we'd get 0 for y, and so on. So we're taking those x and y values and just switching them around. What we want to think about, though, is why it's working this way. So when we did our exponential function, this actually became our exponent. So this 1/2 right here was really the same as 2 to the negative first. When we do our inverse function, what we're doing is we're putting in the answer right here. What it's giving us back is the exponent for the 2. So this is the exponent that we would have for 2 to get an answer of 1/2. Same thing for this one. When we did this, 1 was the same as 2 to the 0. So when we put in 1 for x, we're saying what exponent do we have to raise 2 to get an answer of 1? So our exponent that we'd have to use here would be 0. So this is saying that 2 to the 0 would give us 1. So really we're still kind of going backwards. It's just that this is a little bit harder to wrap your head around because we use this number as an exponent, and now we're going back from the value here and trying to figure out what the exponent would have to be. So for this one, when we did 1 for x here, we did 2 to the first, and that gave us 2. So if we have a 2 here, we could rewrite that as 2 to the first. This is giving us back that exponent right there. We could do the same thing with this one. If we rewrote this as a power of 2, this is 2 cubed. And so our answer for this is that exponent. So it's kind of a hard concept to think about going backwards from an exponential function. But what it's doing is it's coming back and giving us the exponent that we would have had for our exponential function. So what we call this is the logarithm function. And this would be the logarithm base 2. It makes a big difference here what our base was in our exponent. That's how we're figuring out our exponents over here. So if we had a base of 2 in our exponential function, then our inverse function is going to be a logarithm with a base of 2. And the way we write that in math shorthand is we just write it as log, and then our base is a little subscript right here. So if we wanted to write the function notation for this, here's what our function notation looks like. This right here is the name of the function. And this is our input value. So we would write this, our f inverse for this would be the log base 2 of x. So let's kind of go through these and just look at what that would look like in this kind of notation. For this one, if we're trying to take the log base 2 of 1/2, what that means is we want to try and rewrite this number as a power of 2. So if we wrote that as a power of 2, this is 1 over 2 to the first, and we could simplify that with a negative exponent and make it 2 to the negative first. So we've rewritten that, and here's where it comes that the exponential function and the logarithm function are inverses of each other. Each one undoes what the other one does. Another way to think about that is they cancel each other out. It's just like if you have a square and a square root. Those are inverses of each other and they cancel each other out. Or if you had this, it would work that way also. So these two cancel each other out. So we're doing the same thing here. We've got our log function and we've got our exponential function. So really those two cancel each other out. And what we get is this exponent. So our answer for the log base 2 of 1/2 is just -1. Let's do the log base 2 of 8. If we can rewrite that as a power of this base, then we can see right away what the value of this is going to be. So 8 is 2 cubed. Then we've got our log function and our exponential function. The bases have to match for this to work. If they have the same base, then they're inverses of each other, and that means that all we would have left would be the 3. One more of these, if we have the log base 2 of 1, sometimes it's kind of hard to see how you would write 1 as a power of something, but remember that anything to the 0 power is 1. If we have a 1 in there, we can always write it as this base to the 0 power. We can do that, and then these two cancel each other out, and we just get 0. So let's look at what the graphs look like for these two functions, because one that the inverses do is that they switch the x's and y's. Another thing they do is cancel each other out, like we just did here. Another thing they do is on the graph, they reflect across that line y equals x, like we talked about in section 5.1. So let's graph y equals 2 to the x and y equals the log base 2 of x. Now for this, to see how to do this on your calculator, it's going to depend a lot on what model of calculator you have. If you have an older model of calculator, then you might have to use a different method to get this to show up. I'm going to show you what you can do if you have a newer model of calculator. So the first thing to look at, actually let's go back and look at one of these. If we want to do this on the calculator, where you would find this function, it's not necessarily this button right here that says log. That's a specific base log. That's a log base 10. So if you want to find the way to do this on your calculator, press your math button and go all the way down to the bottom of this screen. And if you have this log base function at the bottom, then that's what you can use for this. And this, what this looks like also depends on what model of calculator you have. If you have an older but not too old model of calculator, this will come up on your screen and have this. And in that case, you have to put in the input value first. So you have to put in the 1/2 first and then put in the base. Or you might have it where it comes up like mine did here, where it actually gives you a space to put in the base and a space to put in the input value. So in that case, we put the 1/2, or we put the 2 in here, sorry, and we put the 1/2 in here. So I'm going to make this 2 and then a 1/2. And when I enter, it gives me -1, which is the same answer we got up here. Okay, try that on your calculators, and if anybody doesn't have that log base function, let me know. So again, that was math, and then just go all the way down to the bottom. So if it doesn't have the log base function, then here's what you do. You have to use what we call a change of base formula. And I'm going to write this formula down, but the only time that you're going to use this is to specifically do this. So I'll write it down first, and then I'll write kind of a simpler form of it. All right, so what you're going to have to do if your calculator doesn't have this function is you're really going to have to use this formula and change this to the log base 10, because the log base 10 is the button that says log that's on your calculator. So we're going to use this and change to log base 10, which is just the log button. So to do that, we're starting out with our original. So let's go back to the one we just did. If we wanted to do the log base 2 of 1/2, then we're going to take that here and we're changing it to log base 10. So our new base is going to be the number here. So we're going to change that to log base 10. We're still going to have the 1/2 in here. And then on the bottom, we have the log with our new base. And here we're putting in the old base, which was 2. So a calculator, what this would actually look like is you would just use your log button. So you'd have log of 1/2 divided by the log of 2. So it's not really as complicated, as it seems like. Really what you have to remember is to divide by the log of your old base. So if you just use your log button and then divide it by the log of the base that you started with, then you should get the same answer as we got with that other function. All right, now that we know how to do that, now we're going to go and graph those two functions. So we're going to go back and graph y equals 2 to the x and y equals log base 2 of x. So you can go to your y equals menu. So for this one, I'm just going to put in 2 to the x. And let's graph that just to remind ourselves what that looks like. So it's going up really fast on this side of the y-axis, and on the left side of the y-axis, it's going down towards 0. Then if I go and put in the log base 2 of x here, so here's where I'm going to use that log base function again. So I'm going to put in my 2 for the subscript, and then here I'm going to put in the x. And if you're trying to do this with the change of base formula, this would be log with your log button of x divided by log of 2. All right, so if we graph this, if these two are inverse functions, then we should see a reflection of this one across the line y equals x. So I'm also going to put in y equals x and have it graph that one also. Okay, so there we have it. Our log function is just a reflection of this across this line. So what we get is something that goes down towards the y-axis here. It crosses through the x-axis here, and then it curves over pretty sharply and goes on to the right. Let's talk about the properties of both of these two graphs. This one, I think I mentioned the other night that this actually has a horizontal asymptote, because as we go out this direction, these values keep getting closer to 0. So this graph has a horizontal asymptote of y equals 0, but it's only on the left end. When we do inverses, our horizontal asymptotes turn into vertical asymptotes because we're switching the x's and the y's. So if we have a horizontal asymptote for this one of y equals 0, that means in this graph we're going to have a vertical asymptote, and that's going to be x equals 0. So all we did was we went from y equals 0 to x equals 0. That's one thing that happens. Another thing that happens is that we're going to switch the domains on the ranges when we do our inverse function. So if we look at the domain of this one, this is going on our graph all the way from negative infinity to positive infinity, because as we go this way, it's going to keep going up and out. If we look at our range, though, the values out here never quite get to 0. They're always just a little bit above 0. So our range actually starts just above 0, and then it goes up to infinity. we're going to take those two and switch them to get domain in the range for our log function. Our domain for our log function is the same as the range of this one. That means this is going to be 0 to infinity. That kind of works with what we see here, that we've got that vertical asymptote at x equals 0. But what that really tells us is that there is no graph over here. We can't see one on the graph, but there really isn't anything over here. So there's no graph to the left of the y-axis. Then for the range of this one, that's going to be from the domain of this one, which is negative infinity to infinity. We can see that on this because this keeps going down. So our range goes from negative infinity, and after we go through here and make this sharp turn, it is going to keep going up. It's just going to go up pretty slowly. Our values are going to keep going up. So they go all the way up to infinity. One more thing that's happening on these two graphs, on this one of our points that we talked about was if we put in 0 for x, we actually end up with 1. So this point right here is 0, 1. That's our y-intercept on this graph. When we switch our x's and our y's, our coordinates switch and our y-intercept becomes an x-intercept. That means on this graph we have an x-intercept that's 1, 0. So we took our coordinates here and switched them, so we went from 0, 1 to 1, 0. And that's our x-intercept. That's the only place that that graph crosses the x-axis. This graph doesn't ever cross the x-axis. Well, let's look at another pair of functions. The other night we were talking about the number e, which is an irrational number, and we use that as a base for exponential functions a lot of times. So if we look at this function, where we just have e to the x, then we can automatically say what its inverse function is. That's going to be the log base e of x. This is one that gets used a lot. It has a lot of applications in the natural world especially. So we actually have an abbreviation for this one because it gets used so much. Usually instead of writing it as the log base e, we call it the natural log. And I think the reason that this is ln and not nl is because that this actually came from another language and the words were switched. So this is like log natural, but this is actually called the natural log. So if you see this, then you automatically know it's the inverse of the exponential function with a base of e. And a lot of times with what we do in this unit, I'll tell you that it might be easier for you in certain cases if you just rewrite this as the log base e. It also has a specific button on your calculator because we use it so much. If you hit your calculator, you'll see that there is an LN button on your calculator. So let's say that we wanted to know the log base e of 10. Now, if we were trying to figure this out by hand, that would mean that we'd have to know what power to raise e2 to get 10. That's not something that we would probably know because e is an irrational number. It says 2 point something, something, something. So this isn't one that we're going to be able to usually come up with an integer value for, but we can do that by just using our ln button on our calculator. So if we just do ln of 10, that's going to give us that exponent. Let's say we round this to 3 decimals, that's going to give us 2.303. What that's telling us is that if we take e to the 2.303, that's going to give us approximately 10. The way to remember that these two are connected is if you look at your calculator, this is where we got that e to the x function is it's above the ln button. So if we wanted to do e to the 2.303, we'd be using that button with the second. And that gives us something pretty close to 10. It's a little bit off because we rounded this a little bit. But that's how you can tell that these two are connected, is that above this one is e to the x. So that means that these and these are inverse functions of each other. And this one's easy to deal with. Let's say that we're trying to graph this one. We can just do e to the x. And if you're trying to graph the natural log, you don't have to do a change of base or anything. You can just use the natural log button. So if you want to graph the natural log of x, just do your ln button and put that in. And these two graphs are going to look a lot like the other ones that we just did. So we've got that graph, the exponential function graph up here, and then here's the natural log graph. Okay, then our last pair of functions we're going to talk about is the one where we have a base of 10. If we have 10 to the x, then our inverse of that is going to be the log base 10. This one we already talked about a little bit. This one also gets used a lot, so it has a specific button on the calculator. And we usually write this as just log of x. If you're doing the problems for this unit and you see something that has log and there's no subscript in there to tell you the base, that means it's automatically 10. ln means it's log base e. If you just have log of x, that means it's the log base 10. If we wanted to do the graph of these two functions, now I did the 10 to the x that way, but if you look at your log button, you can see that above that there's a 10 to the x. So this is another place your calculator can help you remember which function this is connected to, because the log button on your calculator, above that is 10 to the x. That's because those two are inverses of each other. So I'm going to go down here and just put in log of x, and that will automatically make it the log base 10. And my graphs are going to look just like my graphs did, only a little steeper for this one because my base is a little bit bigger. The other thing that we usually call this, because it gets used so much, is that we call this the common log. One of the things that we're going to try and get to in this unit is to where we can solve equations that involve either exponential functions or log functions. Because these two types of functions are both kind of complicated, we're going to use the idea a lot that these two are inverses of each other. So one thing that we can do is simplify expressions that have both of these two things in them. So there are two properties that we can talk about, and this just comes from these things being inverses of each other. Did some problems like this where we had a log function and an exponential function like this with matching bases. These two cancel each other out, so we just get x. This also works the other way. So if we have the exponential function and then we have the log function up here, we're still combining an exponential function and a log function, so these two still cancel each other out. The only thing about these two is that the bases have to match. If the bases don't match, then we don't have inverse functions, so this whole thing doesn't work. The other thing that we want to be able to do is take certain kinds of equations and use either exponentials or logs to make them simpler. So what we want to be able to do is convert certain types of equations to exponential equations. If we have something like this, This is going to be hard to deal with when we've got this log in here. We've got the log base 3 of x, and we could probably figure this one out, but it's really easier if we just convert it to an exponential equation. That'll take the x out of the inside of this function and turn it into something else we can deal with. So if we want to convert this one, what we're going to use is the fact that if the log base a of y equals x, then a to x equals y. So what we're doing with this is we have to have matching bases. So we're going to start with the base, whatever it is. In this one, it's a. And then these two things are going to switch places. Notice to get from here to here, the y over there to the other side of the equation, and the x became the exponent. So really taking and just move things around. So the x is going to come over here and be the exponent. The y is going to move over to the other side of the equation. So let's do that with this one. We're going to start out with our base of 3, and then the x and the 4 are going to side. The 4 is going to come over to this side and become the exponent for the 3, and the x is going to go to the other side of the equation, and that way it's not inside of the log anymore. What we just did is just converting from a log equation to an exponential equation. So let's say we have the log base a of 64 is equal to 2, and we want to convert this to an exponential equation. It doesn't even matter that we don't know what this base is. We're going to start with that as our base, and then the 64 and the 2 are going to switch places. 2 is going to come over to this side and become the exponent, and then the 64 is going to go over to the other side of the equation. For right now, we're not even trying to solve these equations that we get. We're just trying to convert from one form to the other form. So all we're trying to do with this is convert it to this form. We're not worried about solving for the a. We'll get to that later. Now let's do another one where we've got a natural log. This is one place that I think it's really helpful if you rewrite this as the log base e. Since it's natural log, it's the same as the log base e of x. The reason I say that is that way you can see easier what base to start with. So we're going to start with our base of e, and then the x and the 2.5 are going to switch places. The 2.5 is going to come over here and become the exponent. The x is going to go over to the other side. So now we have e to the 2.5 equals x. Notice on all of these, I'm not putting in the parentheses. You can put the parentheses in if you want to, but you don't necessarily have to. It's just if there's no parentheses, then if we had something like this, only the thing that comes right after the log is included in the log. So this would be the same as the log of x plus 1. That means the 1 is actually inside of the log. All right, so for this one, because there's no base written in here, that means it's automatically base 10. To convert this to an exponential equation, we're going to start with our base of 10, and then the x and negative 3 are going to switch places. That means the negative 3 comes over here to become the exponent, and the x goes to the other side of the equation. That gives us 10 to the negative third equals x.